Welcome back to another tutorial. We've got method of joints this time, and this is where engineering starts to get a little bit exciting because method of joints is really talking about truss analysis and getting an understanding of what is occurring within a truss system. Okay, the primary need for this is trigonometry, moments, reactions, and addition of forces. So if you think you need to go back and revise any of those things, I'd really recommend that you do that before trying to get an understanding of method of joints, because if you're not well versed in that stuff, you'll probably find some of it a little bit confusing. The objective of this tutorial is to teach you some new knowledge, and that's going to be around Bose notation, as well as identifying reactive forces in a member, compression and tension. Okay, first we've got Bose notation. This is the truss system that we're going to be focusing on in this tutorial. So just a really simple sort of truss system with those three triangles there and our reaction forces that have been indicated there. I don't have the forces pointing down yet, but it's kind of irrelevant to Bose notation anyway. So Bose notation is simply this. And I want you to think about here what I'm actually doing. So I'm labeling the system. It's the spaces around the members. So we're starting on the left-hand side, and we're working with A, working around B, C, D underneath. Okay. We've then got the spaces internal, E, F, and G. That's Bose notation. Now, the reason for labeling a system like this is so that we can then break the system apart and look at the individual joint systems. So we can then call that joint AED, for example. And if we're looking at a member like that, we can then call that member EF. Okay, so that's the reason for Bose notation. Alrighty, let's look at this problem here. Now, in this particular problem, we're given the reactions, okay? Sometimes you'll be asked to solve those reactions, and if you're asked to do that in a situation like this, don't get put off by the fact that the reactions, the forces are coming on top of a system 4.8 up. If we're solving this problem and we're looking at solving reaction right, all that we'd be looking at is our moment from the left, okay, and we would be saying 8 kilonewtons down at this distance, 4 kilonewtons down at this distance, and we could work out our reactions like that. Now, just a little point to note that it doesn't actually relate to this particular problem. If you were given no distances, okay, and you needed to solve the reactions, now only if the triangles that are being used are equilateral triangles, okay, so they're all 60-degree angles, okay, you don't actually need to know the distances to solve the reactions. You could use a number like 3 as the distance, or you could use a number like 1, 2, doesn't really matter. You could call it 2 meters, 1 meter, etc., and you'll be able to solve the problem. So if the system was given as equilateral triangles, all 60 degrees, you don't need to know the distances. In this particular case, the first thing that we need to do is we need to work out what angle we're working with, okay? And we can use our numbers like 3 and 4.8 here to work out what these theta angles are, okay? These are the angles that we're focusing on. All right, so looking at your formula sheet, I mean, if you sort of want to stick with all your SOHCAHTOA trigonometry stuff, you can, but just look at your formula sheet because it's spelled out nice and easily there for you. We've got tan of theta equals opposite over adjacent. That's your trigonometry stuff, of course. And we can do the inverse there to solve the angle. And the angle that we're going to be working on today is 58 degrees. And we're going to be using that angle for all of our scenarios. So just remember all of those bits. We've now got our system complete, complete with Bose notation, and we can start breaking this system up into pieces so that we can solve the members as we go. So the members we're going to be, the joint systems that we're going to be looking at are these ones identified with the red circles, okay? And we'll keep referring back to those. So therefore we've got joint AED, for example. The first thing that we want to do is we want to state your assumptions. So your assumptions that I'm talking about are things like, if we've got a direction going up, we're calling it positive. If it's going towards the right, we're calling it positive. If we've got a direction going down, we're calling it negative. And if it's pushing towards the left, we're calling it negative. Now, the next thing that you need to do is you need to predict whether the member is going to be in compression or tension. And we use arrowheads to do this. Generally, if it's color-coded, you'll often see that it's red for compression and green for tension. This is a really important step, okay, predicting whether it's in compression or tension. And it doesn't really matter if you get it right or wrong. You will see in other tutorials, you will read in other textbooks, people doing it different ways. I'm not saying they're wrong. It's just a different way of doing it. This was the way that was sort of taught to me and makes sense to me, okay? So, for example, one of the other ways that you will see people do it is always assume it's in compression, and then you work out whether it's in tension or not. All right, here is how I've indicated the compression and tension. Now, I want you to think about here, because this might be contradictory or counterintuitive to what you're thinking the direction should be. So for compression, we're pushing into the joint, and for tension, we're pulling away from the joint, okay? So that's the reason for those directions. All right, quite simply, after we've done that, we just work to solve each member by summing the total forces in the vertical and horizontal directions, and we do that separately. Okay, so our first joint that we're looking at is joint AED, okay? We've got the magnitude that we know, which is our 7 kilonewton force pointing up into the system, so that's a positive force. First thing we need to do is we need to predict whether these members are going to be in tension or compression. Now, I want you to just think about like a really basic truss system for a sec with a triangle. We sort of know from our experiences that if we've got a force pushing down on top of our triangle that is going to be pushing out like this, okay? So logic says to me that we've got compression going down and we've got tension at the bottom, okay? But I might be wrong, okay? It doesn't matter. That's the reason why I predicted the compression and tension the way that I have. Okay, for all of what we're doing with method of joints, I want you to remember this key: sum of forces equals 0. Our system's in equilibrium. That's a good day for an engineer where our bridge is not falling down. Remember, if your system is not in equilibrium, the bridge is falling apart for some reason. So we don't want that to happen. Sum of forces vertical equals 0. All right, if we've got forces coming up, then the forces coming down have to be equal and opposite, don't they? Same as if we've got a force coming from the right, we must have a force coming from the left to equal that out and cancel to 0. It just makes sense. All right. So first thing we're going to look at is joint AED. Now, to start with, we're going to be solving member AE by looking at summing the forces in the vertical direction. So, sum of forces vertical equals 0. These first ones, I'm going to walk you through exactly how I've solved it. So, we've got 7 newtons in a positive, pushing up, and we're going to take away member AE, all right? But it's actually the vertical component of member AE, isn't it? So looking at our formula sheet, okay, we've got minus AE, because we're saying that it's a down force, sine 58, because that was our theta angle that we're working to. All right, so we've got plus 7 minus AE. Now, unfortunately, we can't plug that into our calculator because there's no AE button on our calculator. So we need to isolate that member AE, don't we? Now remember, the mathematical function, the minus, it's going to go with it. So when we shift it to the other side, what happens? It becomes a positive. So now, when we rearrange that formula, we've got a positive AE equals 7 over sine 58. Now, the really important thing to remember here, guys, is the positive and the negative isn't actually really talking about, I know that I said at the start that we're stating our assumptions about down and negative and up and positive and stuff, but it's not really talking about that. What we're going to use the positive and negative for is to validate whether our prediction was correct. Okay, I want you to remember that. So we've rearranged it, and we've now got plus AE equals 7 over sine 58. So that then gives us 825 kilonewtons, and it's a positive value. Now what that positive value does is validates that the original prediction of compression is correct. Okay. If you like, you could try by starting backwards, and you could say plus AE, shift to the other side makes negative. You could work that out. It should work out the same for you. Okay, we're validating here that our prediction of compression is actually correct. So we've done that. Notice that we've ignored ED, remember ED to start with. Okay, the reason we've ignored that is because we're only looking at the forces vertical. There are no forces vertical in member ED because it's horizontal member at 0 degrees. Okay, so now is our chance to use that. We're going to use, oh, there we go. There's our 825 kilonewtons labeled on our system. So we're going to solve for member DE now. Okay, and we've got sum of forces horizontal equals 0. It's in equilibrium. We've got a negative 8.25 from our member AE. Okay, and remember it's negative because it's pushing in towards the left. All right. Cos 58, because it's the horizontal component of AE that we're looking for. And we're going to add to that member DE. And we're adding to that as a positive because it's moving the other way. Okay. Alrighty, rearranging that one. The positive DE becomes a negative DE. So we can punch that into our calculator now. Negative 8.25 cos 58 equals negative DE equals negative 4.37. Now, when we've got two negatives, the double negative cancels out. So therefore, member DE equals 4.37. It's a positive value, and that validates that our tension prediction was correct. All right. So if you end up with a negative value, that will just tell you that your prediction was incorrect. If you end up with a positive value, that tells you that your prediction was correct. All right. So there's our 4.37 kilonewtons pulling in tension away from our joint. We move through. Key to remember, sum of forces equals 0. We've now got some other values that we can put in. We've got 8 kilonewtons, which was acting down on our force system to start with. And we've already solved member AE. So we've just written that there as 8.25. I've gone and made my predictions there. We worked out that AE was in compression, so it's pushing into the joint. I think member EF is also going to be in compression, based on what I said to you before, and I'm predicting that BF is in tension. So this joint is now called ABEF. Solve for member EF, and the reason we're solving for member EF is because we're looking at the sum of forces in the vertical. Okay, we work our way through the formula, the equation, like I've shown there, and therefore we end up with 1.18. It's a positive value. Okay, those negatives have cancelled each other out, so we end up with a positive value, which again validates that our initial prediction of compression is correct. So there's our 1.18 kilonewtons. Looking at our total sum of forces in the horizontal, we've now got 8.25 cos 58 minus 1.18 cos 58 plus member BF. We work our way through. We can punch that into the calculator and we end up with our answer, positive value, 3.75 in tension. Okay. Now remember guys, for this method, the way that we're doing it, a positive value validates your prediction. Some other tutorials will say a positive value means compression and a negative value means tension. Okay, that's not the way we are doing it. The positive value validates your prediction. This one here, I'm just going to talk to you through this one a little bit differently. Okay, a little bit more closely. We've solved member DE, and we know that it's in 4.37 kilonewtons in tension, pulling away from the joint. We solved that one. We've also just solved member EF, and we know that that's in compression, pushing into the joint. Now we're looking at our joint system DEFG, and when I look at the member FG and the member DG, I've predicted that FG is going to be in compression, pushing into the system, and I've predicted that GD is in tension, pulling away from the system. These might be wrong, okay? Well, I've just realized that I've given you the answer there of GD. I shouldn't have included that one yet because we haven't actually solved that problem. Okay, so we're looking at member FG here, solving the sum of forces in the vertical. We've got negative 1.18 sine 58. Okay, that's taken from EF. And we're going to take away here FG sine 58. Now the reason I'm doing that is because I have predicted that it's pushing into the system. I'm predicting that the force is coming down, which means that it's a negative value. As I work my way through, when I go to rearrange this, and I go to put the FG on the other side, okay, the two sine 58s cancel each other out, which means that the FG, when we relocate it, becomes a positive value. And if we then look at that, that's saying positive FG equals negative 1.18. So a negative value actually indicates that that initial assumption or prediction of compression is incorrect. Okay, it doesn't matter. It doesn't mean that I'm incorrect. It just means that my initial prediction was incorrect. Therefore, FG is actually that value, that magnitude of 1.18, but it's actually in tension. And I've gone and corrected that by shifting a green arrow on my diagram there. Okay, so that was a genuine process that I went through initially. All right, but I think it's important to show you how that happens. All right, and it doesn't matter if you get it wrong as long as you get it right in the end. So we've now got that 1.18 as a pulling force away from our joint. Now, when we're looking at the last member here, GD, all right, we're looking at our sum of forces in the horizontal. All right, we go through and we work out that we were correct. It is in tension. Go through all of those formula and equation, and we get 3.12 kilonewtons in tension. Alrighty, we're almost done with it. All right, this is actually the last of the joint systems that we need to look at. So we've got the last one of our 4 kilonewtons coming down. We've got the values that we know of BF 3.75. We already verified that it was in tension. And we've got FG 1.18 kilonewtons. We've already verified that it's in tension. So we're here to solve member CG. So we're looking at joint BCFG. Looking at solving the sum of forces in the vertical. -4, because that top value is pushing down in 4, minus 1.18 sine 58. We're only looking at the vertical forces, plus CG sine 58. Negative CG, so our plus CG becomes a negative as we switch the sides, equals -4 minus 1.18 sine 58 over sine 58, gives us two negatives, double negative. Negative CG equals negative 5.89. Again, they cancel each other out. Therefore, member CG equals 8.89 kilonewtons. We've validated our initial prediction that it's in compression. So there's our response. Now, there's what our force system looks like. We've gone and solved all of those members. Now, you might be asking, but what about the reaction on the right, the 5 kilonewtons? You haven't taken that into account. How come you've ignored that? Now, the crazy thing about this is that the maths equals out. If you were to flip this system around and start with 5 kilonewtons pushing up, go and try it for yourself. You're going to find that that member, CG, even if you do the whole thing backwards, still equals 5.89 kilonewtons in compression. That bottom member, I think it was DG, still equals 3.12 kilonewtons in tension. Okay, go and try it out for yourself. But there we have solving that whole truss system. That's what we call truss analysis. All right, working out what's happening with each of the members throughout the whole truss.